Hey, what's going on, everybody? My name is James, and today I want to make a video talking about a little bit of a different topic, but still related to the electric vehicle conversion that I'm doing. So, I know those of you who are likely watching these videos are interested in doing one of these projects yourself, and there's a few things that you should probably know before going into this in terms of things to look out for and the equations that you need to know to be able to figure out the components you need for your conversion. So there's a few things that I want to go over, such as what's a kilowatt, how do you calculate kilowatt hours, how do you calculate kind of the estimated distance that you can get out of a car, and just kind of a few other terms that I think are going to be extremely important in your venture into this space. So I'll go over a few, and I think these will definitely help you when you're trying to put together a good parts list for your car. So the first thing that I want to cover is volts, and that's going to be an important term in your system because the voltage of your system is going to really dictate a lot of the components you're going to be using. So it's going to dictate likely the motor you're using, the controller, the wiring, the contactors. There's a lot of things that rely on this specific number. And so the volts relates to a few different things as well with calculating things. So we'll put volts over here. Now, in terms of the, I guess, more road-going components, what that actually relates to is your top speed. The higher the voltage, that means the higher your electric motor is going to spin. So we'll put that as electric motor top speed. So that's kind of like the horsepower in your car. Horsepower will really dictate how fast your car can go. And now there's another part of that, which is torque. So you might wonder, what exactly does that relate to? That's actually going to be the amperage, or amps. So in this case, we have so the amperage, like I mentioned, is going to be torque. And if you don't know what torque is basically how hard something can twist. So if you think about taking off, the top of a jelly container or something like that, you apply a lot of torque, you put a lot of pressure in a rotational motion, and that allows the lid to come free. Similarly, if you have a lot of torque, that means your wheels on the car can push very hard in the forward direction, and that's going to get you going faster. It's going to get you going up hills, and that's just kind of going to dictate the performance off the line of your car. So that's kind of what amperage is going to signify here. So we'll put that as kind of the off the line performance. So now the next thing that's important is going to actually be multiplying these two items together, voltage and amps, because that's going to give us a very important number in the electric vehicle world, and that's going to be our kilowatt, or watts. So voltage times amps is your watts. So it's pretty simple. You have V times A equals watts. And in this case, we're likely going to have very high numbers for these voltage and amperages. So more times than less, this is actually going to be kilowatts, so 1,000 watts. So kilowatts, that's 1,000 watts, and that is going to kind of dictate some of the performance aspects of your car, because if you think about it, if you have volts being the top speed, your amps being how fast it can get to that top speed, if you're multiplying them both together, it's going to give you a very good metric to figure out exactly what you should expect from your car. For example, the electric motor that I'm using in my conversion has a peak of about 150 kilowatts. So it's a 144 volt system, and I'm running it hopefully at about 1,000 amps. So if we have, let's do this here, we have 144 times 1,000 amps volts. So that's going to give us about, that's pretty close. So that's going to give us 144,000 watts. Now I mentioned everything is probably being kilowatts just to keep this a little bit simpler. So kilowatts is dividing this by 1,000. So if we put that over 1,000, that is going to equal 144 kilowatts. So 144 kilowatts is the combination of your volts and your amps, and that's a pretty torquey engine, and I think it's going to definitely propel my car faster than I'll ever be able to use. So the next part I want to talk about is relating to the battery packs. It's actually very similar to these equations, and there's only a slight difference that you'll notice. So volts of batteries, that doesn't change. The voltage is going to be constant. We don't need anything new for that. So we talked about amps. Now, if we look at amps from a little bit of a different perspective, they can achieve different things, I'll say. So amps, when you're talking about an electric motor, is going to be, again, that pulling force. But amps in terms of batteries is kind of the amount of power that they're outputting. So the higher the amperage, the more work that they can do. So there's another metric that comes out of that called amp hours, which basically, I don't quite understand the exact way it is calculated, but it involves taking a battery and applying a constant source, say an electric motor that's running at a constant speed, and you see how long it takes your battery to drop a certain amount, and you're going to calculate an amp hour using that, basically telling you how far your battery will drain over the course of an hour. So let's talk about car batteries, for example. I would say the average car battery that's not a deep cycle marine battery is probably going to have a usable amount of about 40 amp hours, and those are at 12 volts. So let me kind of put this up here and we'll do some calculations. It's going to be very similar to this, but you'll notice some key differences because we're going to have some new units. So voltage is going to be the same for batteries. I'll just label this motor. So let's kind of fill this out. So if we have a car battery that's going to have 12 volts, I don't know, we'll use kind of a higher end one that has 1,000 cranking amps, so we'll say 1,000 amps. But it can't output that much for that long. So what a car battery usually has as its lead acid is kind of a small number of amp hours. In this case, I'll use this kind of an average of 40. So that's kind of a safe figure so you don't overrun the battery. So what can we do with this? We can still calculate the total number of kilowatts of this pack. Now, you might notice we have these new units down here of amp hours. So we have kind of a time aspect to it. If we take our volts and multiply it by our amp hours, we're going to get a little bit of a different metric here. We're going to get kilowatt hours. So now if we take our voltage and we multiply it by our amp hours, we're going to get about 480 watt hours. So you can notice that this is definitely a little bit similar to what we did here, where when we multiplied voltage by amperage, we got something in watts. But now because we have the element of time, hours, we have amps over a duration of time. So it's a little bit different. And that time becomes important when we talk about how far our car can go. Before I can make this full calculation, there's something else that we do need to calculate as well, and that is going to be how many watt hours our car takes to actually move. Now, I'm going to calculate kind of the worst case scenario number, so this is going to show you what is going to be kind of your minimum range with the vehicle that you're using. Likely you'll get further range, but this will kind of calculate for if you had the worst driving behavior with it. So this way, you will know what is the minimum that you're capable of. So before we're actually able to do much more with this, we need to actually calculate another number that's going to be more important. Okay, so now we have this number of 480 watt hours. There's another number we need to calculate first before we can actually do anything significant with this. What we're going to calculate is how many watt hours it takes to go a mile in your car. Thankfully, this is actually a very simple equation. There is a few other ways that you can calculate this, but I'm going to give you a very, very generic one that'll give you kind of the worst case scenario. So this is going to be the minimum number of miles you can go on your battery charge. You'll likely get more than this, but this is going to give you that minimum, like worst case worst driving habits number that you'll get out of your battery pack. It's pretty straightforward. Basically, you just take, let's see, we'll label this car now, this car section. So you take the weight of your car in pounds. So in my case, it's 3,500 pounds. I know it's a little bit heavy, but we're working on it. So that's pounds. And we're gonna just divide that by 10. And that's going to give us 350 watt hours per mile. Oops, per mile. So I know that this seems kind of like a weird jump to go from pounds to watt hours per mile, but it's a very rough estimation and it works. So I'm gonna trust that. So you might notice now we have something in watt hours and something in watt hours per mile. And if you kind of think about how division works, if we want to get miles, we just divide these two together. So let's take 480 and we're just going to divide that by our 350 watt hours per mile. And now it's not going to be very far, because if you think about what we're doing, we're trying to run a 3,500 pound car on a 12 volt battery with 40 amp hours, which is really nothing in the grand scheme of things. But let's see how far we can get. The answer to this is about 1.37 miles. So now we have this answer in miles, but there's a very big thing you have to remember about batteries that we need to account for here, especially if we're using lead acid batteries. Now we can do this, I'm going to redo these calculations for lithium, but for lead acid, you can't really use all of this available resources in there just due to their chemistry. You can use about 50% of it, and even then you don't want to use that full amount, because after that 50% mark you're going to damage the battery. It likely won't put out as much power, it won't recharge, and there's a chance that it could explode if it's really getting a lot of stuff pulled from it. So what we're going to do with that then is we're going to actually modify our number of watt hours, because again, this is the maximum number of watt hours we can get from this battery, but we don't want to take all of its watt hours because then it just won't work anymore. So we're going to actually take that 480, I'm going to erase this here a little bit. We're going to take that 480 and we're going to just divide it by 2, because I said you use about half the battery capacity is recommended. So we're going to get 240, oops. So we're going to get 240 watt hours. But even then, remember, this is basically the maximum recommended usage, and we don't want to push those boundaries. We want still a little bit of headroom. And so I would multiply this number by about 0.8 or take 20% off of it. So if we multiply this by 0.8, that is going to give us, that's going to give us 192 watt hours. Now that's a very significant decrease, and you can see why people likely don't go for lead acid when they build an electric car. I would say it's good for the prototyping phase when you want to see if everything works, but when you're going to actually have a full-fledged car, definitely go with lithium, because with lithium, this step can be skipped right here where we divide by 2. So if we did that, you'd likely end up with still about 400 watt hours instead of 192. So you're getting much more capacity and much more usage out of lithium. While it is more expensive, you're going to get, again, much further range with that. So for example, if you take this 192 watt hours now and we divide it by our 350 watts per mile, you can see it's not even going to go a full mile with that. It's going to be like half a mile of that. So that equals about 0.548 miles. A very, very significant decrease from that 1.37 miles we started out with. And again, this is why I would really recommend using lithium, and I will eventually do that with my car, but I'm going to start out with the lead acid style here and work my way up to that, because it is an expensive thing to invest in right off the bat. So let's go back and I'll do this for maybe a more realistic system that you'd be using in a electric car. So I'll try to do mine here. So I'll erase some of these numbers here. So now to put this into perspective, let me do some of these calculations for what I would like to do with my car right now. So I still plan on doing about 1,000 amps because that's the amperage of the controller I'm looking to get. And as I mentioned before, I have a 144 volt motor. So I'll put 144 up here now, volts. And the amp hours of the pack, I don't think I've necessarily decided on what I want to do yet, but I think to start off with for prototyping, I'm going to use lead acid and then I'm going to move to lithium when I can save up for that. So I don't know, right now if I'm using 12 lead acid batteries, we'll do 12 times 40. So now you can see that this is actually going to be a much more powerful system, because if we have to multiply amp hours times 144 volts, this is going to be a pretty massive number. We're going to start getting into kilowatt hours, and you'll see that this is actually a much more realistic system now. So let's do this calculation here again. So 144 times 480 volts, and then amp hours. So if we take 144 volts and multiply it by 480, that's going to give us about 69,000 watt hours, or alternatively 6.9 kilowatt hours. So now I mentioned that this is going to be lead acid, so we have to do those same calculations again, divide by 2, multiply by 0.8, and we'll get the kilowatt hours of this sample pack right here. So divide by 2, multiply that by 0.8. So that is going to be 2.76 kilowatt hours. So again, a substantial decrease in total battery capacity, but for my usage of prototyping and making sure the car actually moves, that's going to be fine until I can upgrade to lithium later. And again, we'll do the same thing where we divide it by our car estimation, but remember, this is watts per mile, this is kilowatts. So we have to divide this by 1,000, and then we can divide these two together. So we're going to divide this by 0.350 kilowatt. So with this battery pack and my car, we're going to get about 7.7-ish miles. So not very far, but for my usage of testing, that's going to be fine. And if we want to do one more calculation, maybe change it up a little bit, maybe use a different car here. So let's say somebody's doing like a Volkswagen conversion, like the Beetle. So that's going to be a much lighter car, so we're going to go with about 2,500 pounds. Again, over 10, it's going to give us 250 watts per mile at highway speeds. And so we'll keep it at 144 volts. We'll keep the same 1,000 amp controller. But the amp hours is going to be different because lithium can support a lot more capacity in the same amount of space. So let's say they're going to have, I don't know, 600 amp hours. It's going to kind of be the same amount of kilowatts as like a Tesla, we'll say. If we do this math again, 144 times 600 is going to be about 86 kilowatt hours. Kilowatt hours. So this is basically equivalent to like a Tesla Model S P85 or something like that. I don't know if they'll be able to fit all of this in their Beetle, but if they could, this would be a really cool car to work with. So we'll do again the same calculation that we did before, but because we don't have to worry about the lead acid conversion, we don't have to divide this by 2 anymore. But we can go through and multiply it by that 0.8, because that 0.8 again refers to the safe capacity that we can use. We're leaving that extra 0.2 or 20% just kind of as some residual, just because if you drain lithium completely, again, it's going to damage the cells, they're not going to recharge. This is just playing it safe and ensuring that we are getting the full potential without ruining our very expensive battery. So now we're at about 69 kilowatt hours, sorry. And we'll do that last division again, but remember, kilowatts is not the same as watts. We're going to have to divide that by 1,000. So we're going to divide 69 by 0.250 watt hours. And that is going to give us about 276 miles. So that would be a fairly significant performing car. Now, this would be a very expensive system because lithium, especially 600 amp hours worth of lithium, is going to be pretty penny, but in a car like this that's pretty lightweight, uses less watts per mile, and is using more efficient battery technology, you're going to see a huge performance gain in your final results. So definitely keep that in mind when you're designing your car, because that's just going to be a very significant thing, the difference in battery chemistry. Again, I think lead acid's good for testing, but in the real thing, you're going to want lithium because that's going to give you a lot more range. If you did this with lead acid, this would be chopped in half. So what is that, 140 something miles, 150? It's much less than what you get with lithium. So I think this is really a good starting point if you are looking to figure out where to start with the components you're going to be looking for in your conversion. I would recommend getting higher voltage stuff if you want highway speeds, because that's going to dictate how fast your motor spins again. Now the amps and stuff, that can be kind of manipulated a little bit depending on what you're looking for, but again, remember the kilowatt is going to be important. So one last thing that I want to touch on before I finish up here is, if you want to kind of put this into a more mechanical perspective, I'll say, what you could do is actually convert these kilowatts into horsepower. So if you want to equate it to the engine your car had previously to ensure you're having similar performance, you can actually convert this into horsepower and compare it to, again, the engine you had previously, and that'll kind of tell you if it'll perform better or worse. So it's a pretty simple equation. You just divide it by 0.746. And in this case, that's about 193 British horsepower. So that's a pretty, decent number. I would say that actually beats out the engine that's in my Beamer currently. It has 180 horsepower. So this will be a pretty peppy car, especially with all-wheel drive. So I'll be interested to see how this all goes together. I hope you guys found something valuable in my work here today. And speaking of that, I'm considering starting up something like a Patreon, because I feel like there are a lot of resources I can share with you guys to help you through your conversion process. But right now, just my time is very limited, as you might be able to tell. I'm currently at college, and so things definitely get a little bit tight. But if I was able to start a Patreon and have kind of a little bit more disposable income to put towards this project, then I could give you guys much better content and resources for you guys, so it'll make your lives a little bit easier. And one last thing, I do want to just promote my website, electricbimmer.com, where I'm doing kind of more frequent updates on that, because these videos are, again, larger chunk progress updates, because there's a lot more work that goes into this than just blog posts and photos. So check that out below if you're interested in seeing how this project is going. But that's going to be it for me today. I hope you guys enjoyed. Subscribe so you don't miss anything else. Catch you guys in the next one. Peace.